Hi, welcome to this series on the DH parameter selection. Today I'm going to talk about how we select DH parameters in real implementations, for example, in Bouncy Castle, which is an open source software. So I will look into it. I will show you how the DH parameters are validated at runtime. In the previous session and the session before that, we talked about safe primes like the primes with particular structure like p equal to 2q plus 1. We also looked at generalized safe prime p equal to jq plus 1. J is a large even number. We compared the performance of a regular safe prime with the generalized safe prime, and we observed that the generalized safe prime is significantly faster than the safe prime. However, in real implementations, most of the time, the second option that I mentioned here, this safe prime p equal to 2q plus 1 is actually used. It turned out that there are some benefits of using standard groups as opposed to generating our own groups. So I will show you things become much faster if we assume the groups are one of the groups published in RFCs, for example. Okay. So let's get into the demo quickly and wrap up this discussion. So let me run this. Okay, it took about 2 seconds when I'm using the generalized, one moment, the regular safe prime, right? Let me check what I'm doing here. This is generalized. I see here J is very large number. Otherwise, the regular safe prime will be J is 2. Okay, so here it took some time, of course. Let's look at the regular safe prime. In the regular safe prime, we can quickly measure that as well. When we do the Diffie-Hellman key exchange, with the regular safe prime, it's kind of slow. It took almost close to 4 seconds. It's double. Okay, and we got the shared secret here. The reason is this, actually. There's one statement, if I can show you that, that caused the problem. The problem is this. When Bob is checking the primes he received from Alice, he's checking whether the numbers P, Q are actually primes. So these two statements in particular are expensive statements in terms of runtime. Okay. So if we can, let's say, we completely ignore this. Okay, we don't check whether the received numbers are actually primes and the group G is a generator and so on. For a moment, let's skip this part. Okay, what kind of benefits do we see? Let's try this on both generalized and safe primes. Okay, let's try this now on the regular safe prime. As you can see, it was very quick. We got the answer very quick. Let's try this on generalized one. You will see that it will be also much faster, actually. Let's try this. Yep, it was extremely fast, right? Comparing to the regular safe prime. The reason for this speed up is just because of those if statements that check whether the primes, the numbers P and the G and the Q and all of those numbers are good numbers. You know, they're not backdoored or they're not prime numbers. The group G is actually generated by G. The group is actually generated by G of order Q. These statements actually are pretty expensive. In particular, this one and this one cost this problem. Okay, so in real implementations, actually, we don't check whether P is a prime, Q is a prime, G is a generator. The reason is that in a moment I will show you by taking Bouncy Castle example. Let me take Bouncy Castle. Okay, let me copy and paste this. I will show you how Bouncy Castle handles Diffie-Hellman parameter validation. Let's go to line number 81. I'm going to show you a portion of the Diffie-Hellman key exchange. Line number 81 is the function called process server key exchange. So when the server is sending this data to the client is going to verify, you see here DH parameters receive and verifies it, right? Let's look at the code of verify DH parameters. What is it really doing? We can look at it at line number 484 of this portion of the code. Line number 484. Line number 484. 484. Oh. You see here, all of these are list of primes. In a moment we will show you validation. 484. Yeah, here it is. So it reads the parameters from the input sent by the server to the client, right? And then at line number 484, it checks whether the parameters are good parameters. Okay, so how is this checking happening? Let's look at that code. That portion of the code is line number 68. Okay. Okay, so line number 68 actually verifies the group. Let's see. Here you go. So it checks whether the parameters have some basic properties, like they have minimum prime number of bits and checking the groups. Okay, these two are important, right? So let's look at check minimum groups, check minimum prime bits and the check group. Okay. So what it's doing actually is simple. This is a default DLS DH verifier. In the static block, they add the list of standard primes that are published in RFCs, different RFCs, right? Request for comments. I shown one in the last presentation. Those are all added to the list. So if the incoming element, where is this incoming element? Okay, here it is. Check group. You can see check group function goes through the list of groups that are stored inside this class and compares against the parameters that were sent by the server to the client. If the parameters are in the group, then they say, yeah, it's a good group, otherwise it's a bad group. Something similar happens here. It checks the incoming primes minimum prime bit size, and it compares against the expected minimum bit size. Okay, that's all. In fact, to be more precise, it looks at the incoming parameters and look at the prime P and checks whether the bit length is more than the minimum prime bit length that we would like to have. Okay, so this is how the DH parameters are actually evaluated. So at runtime, it is not really checking whether the primes P, Q, and G. P, Q are primes, G is a generator, G itself is a generator, and so on. Those things are all hard-coded anyway. So you can see here, it's taking data from all of these RFCs. These are all the RFCs. It hard-codes that into the list. Okay, that's basically it. This is how they achieve this in Bouncy Castle. Okay, all right. So what I wanted to say is that if we use standard groups, we can avoid some of the expensive checks, whether some number is a prime number or a subgroup is a prime order group, and things like that are already checked. So there's no need for us to do this check at runtime every time a connection is established. That's the reason why both the safe prime and the generalized safe primes were actually slow during the previous demos that I did. Although it's worth to recall that the generalized safe prime is much faster because of the small exponent, right? The exponent that we deal with, here maybe this picture will help us to recall. In the regular safe prime case, the exponent x that we are seeing here is a very large number, like 20, 48 bit and so on. But in the case of generalized safe prime, X is only 256 bits. So it's 8 times, at least 8 times smaller. So that's the reason why we got such a quick turnaround when we used the generalized safe prime. Okay, thank you very much.